The Robinson R22 power plant. Another word for power plant is engine. We're particularly talking about the engine that drives the main rotor and the tail rotor. Of course, the engine also drives things like the alternator. And let's see, I'm sure it spins something else. The engine that's in the R22 Beta 2, which is the only aircraft we're going to fly here at Guidance, is made by Lycoming. The aircraft is made by Robinson. The engine is made by a different company, Lycoming, and it's an O, that's an O or Oscar, -360-J2A. Of course, we always typically refer to it as an O360. The O stands for horizontally opposed. That is, if we look at the engine from one end, the cylinders stick out on the sides. That is, the cylinders oppose each other. And the 360 stands for the fact that it has 360 cubic inches of displacement. Every time the engine rotates through one full cycle, it'll suck in a volume of 360 cubic inches of air. And if you're used to like a Chevy 350 small block, you could say it's about the same size engine on how much air it pulls in. It's got 4 cylinders. It's kind of like an air-cooled VW. It doesn't have any gearing. That is, the shaft comes out of the engine. The crankshaft that you bolt things onto is spinning the same speed as the engine. You blow air across the cylinder fins, and you blow air across the oil cooler. It's air-cooled. And the O360 runs off of a carburetor. It's not fuel injected. If it was fuel injected, there'd be an I here, and it would say IO360. And normally aspirated means it doesn't have a turbocharger and it doesn't have a supercharger on it. So the higher we go in altitude, the less horsepower the engine can develop. Here's a picture of an O360 in a Robinson R22 Beta 2. You can see can't see that much of it. You can see the squirrel cage that pulls air in and blows air across the cylinders. You can just see the bottom of one cylinder here, and the air is going to get blown across it. You can see the rocker covers. You can see the silver tubes come out from underneath the engine where the intake air comes in, and you can also see the exhaust duct going through the exhaust ducts and the muffler. Well, it's not really a muffler, it's a heat shroud. These engines are straight pipes. If you follow this pipe all the way through, there's no restriction. There's no restriction at all. It's hard to see it right down here, but the carburetor is down here. Here's a picture of a Lycoming O360 outside of a helicopter. Here is the starter ring gear, which we have in Robinson R22s. You can just barely see the starter, and that ring there is so the starter can connect with the engine and make it spin. You can also see the magnetos. These two black things right here are the magnetos. They're generators that produce electrical power and go to the spark plug. Each cylinder, you can see the cylinder here. There's one here, one here, one here, one here, and each magneto operates one set of spark plugs, one for each cylinder. And this gizmo right here is an engine-driven fuel pump, which we do not have on an R22. R22 fuel systems, the tank is above the engine and gravity pulls the fuel down to the carburetor. Here you can see that the intake ducts or the induction pipes going into the engine look like it goes into the bottom of the engine or the oil sump like on a regular carb, and in this case there's that tube actually keeps going in and then comes down, and then the carburetor is mounted underneath, so it's not like we're mixing oil with our intake air. Here's another picture of a Lycoming O360. You can see the ring gear. You can also see what looks like a pulley here, and we have those on R22 Beta 2s that lets us have an alternator belt, a belt to go to the alternator. Now you can start seeing better. The carburetor would be bolted on under here, and airflow would go through the carburetor and then up the intake tube into each of the 4 cylinders. You can also see the oil filler neck right down here, which actually goes all the way down into the oil reservoir. And again, of course, magnetos. Sometimes magnetos are painted black. Many times they're painted black. Sometimes the aluminum is bare. And here's a picture again from the other side. Finally, a carburetor. So the airflow would come through here through a duct into the engine, into each cylinder. So you can see this case here is made out of aluminum, and the fins are made out of aluminum, and these fins right here are made out of steel, and inside each cylinder is a steel barrel that goes all the way around, so the piston goes up and down inside the steel barrel. And there's a camshaft in here with lobes on it with bumps, so it pushes on this rod right here on a rocker arm, and then this rocker arm pushes down on a valve. So whenever this lobe comes around and pushes on the push rod, it pushes on the rocker arm and pushes down on the valve, and that valve opens and lets air in. Of course, we have a whole nother one. There's another one down in here, and it runs the exhaust valve, which would let exhaust out. Of course, in this picture, the exhaust tubing is not shown. And here's you can see the starter motor. You can see these teeth right here. This engine doesn't have a ring gear installed on it at the moment, but these teeth move outward and engage the starter ring gear. Here's another picture of Lycoming O360. Looking at it from the top, you can see that this cylinder right here is offset a little bit from this cylinder right here, this cylinder right here, and this cylinder right here. So the crankshaft in here and the connecting rod going up to the piston, the connecting rod for this one attaches to the crankshaft a little bit off. Here, the connecting rods come in, going to connect, the connecting rod's going to come in and connect. And of course, there's a piston in here, piston in here, piston in here. So they have to be offset just a little bit. And you can see this part right here is the accessory section. You can bolt things onto it. Here's a Magneto that is still aluminum. You can see that one that didn't paint. Here's a picture on an R22 Beta 2 with the side cowling off. You usually can't see it this well. This box down here is the battery. You can see the battery. You can easily see one of the spark plugs coming into the top of the cylinder. Another spark plug comes into the bottom of the cylinder. All aircraft engines that are certificated, that is, have to have 2 ignition systems. We'll get to that here shortly. You can see where the intake air is coming in, and you can see where the exhaust is going to come out. And you can see the baffling that you can is partially removed here. So the air that's going to come in is going to get blown through those fins. It's going to get blown through the fins to keep the engine cool. And here you can see a Magneto bolted on. Here you can see the accessory section of the engine. This white thing right here is the oil filter. We'll talk more about that when we get to the oil system. Engine RPM, of course, it's on the tachometer, engine tachometer, rotor tachometer. E is for engine, if you're not sure. And the tachometer is calibrated in percent. There's a percent sign down here. So it's not in 2,000, 3,000, 4,000 RPM. It's in percent RPM at 104%, 102, 104. So that would be at the top of the green arc. At the top of the green arc, it's 2652. Interestingly enough, the red line, if you look in the maintenance manual, is 2,700 RPM. So even at this top of the green arc red line, the engine could actually spin faster. So this is actually, this right here, this is a Robinson helicopter limitation, which of course we're going to abide by. This engine runs off of gasoline. You can have 2-stroke engines, you can have 4-stroke engines. Our engines are 4 strokes. They get a lot better fuel economy. They tend to last longer. The 4-stroke was invented by a guy named Otto. That's his last name. You can run 2-stroke engines in some airplanes. Most of those are experimental airplanes. Most gasoline engines by Lycoming and Continental are 4 strokes, and there's 5 events. So there's the piston goes up and down inside of a cylinder. So here's our piston. It goes down, connects to the crankshaft, and it goes down and up and down and up. So we get 4 strokes, but on the way back up, the spark plug fires. So we'll get to that here shortly. The intake stroke, the compression stroke, and just before the piston gets all the way to the top, the ignition fires, the spark plug fires. Then we have the power stroke and the exhaust stroke. We'll take a peek at those. Intake stroke. Intake stroke is when the exhaust valve is closed. This one right here is the exhaust valve, and you can see a camshaft with a lobe or a bump on it. It's not pushing it down, so this is closed right now. The intake valve, you can see this cam here, the lobe or the bump on it is pushing down, so this is open. So the air-fuel mixture comes in from the carburetor. It's got fuel and air in it, and of course the piston started way up here, so as the piston goes down, it creates a vacuum, or at least it certainly creates a lower pressure, at least low pressure. And so if the air on the other side of the carburetor is a higher pressure, it's going to pull the air through the carburetor, and the carburetor puts fuel in it, so now coming in is evaporated fuel and air. So the piston's going to go all the way down, the crankshaft is going to be rotating. The compression stroke, when the piston gets about all the way down, the exhaust valve is still closed, and the intake valve closes. That is, the camshaft is rotating, the bump or the lobe is moved away. This is spring loaded. It doesn't show a spring, but the spring pulls it back up. So now no air or fuel can escape. This second stroke, number 2, is the compression stroke, and that's where the piston gets pushed back up by the crankshaft. The crankshaft is rotating. It pushes through the connecting rod to the piston goes up, and the pressure goes up. We have an increase in pressure now. And the reason we want an increase in pressure is because the higher the pressure that we burn the fuel at, the more fuel efficient it is. If the pressure is low, we won't be able to extract as much energy. When that piston gets almost all the way up, let's just say that the highest point that the piston can get is right here. A little bit before that, just a little bit before that, is where the ignition is going to fire. The spark plug is going to be powered off of the Magneto, and we're going to get a flame in here, and of course it's going to start burning. But the distance right here is pretty small, only about 1/8 of an inch, and the time it takes to go from here to here is really small, very, very small portion of a second. And we need that time just to get the fuel burning, because what we really want to have happen is, in the power stroke, this fuel burning is going to increase pressure. We're going to have an increase in pressure quite a bit, and we want that increase in pressure because it's going to apply a force to the piston and push it down. Piston through the connecting rod is going to push on the crankshaft to keep the crankshaft spinning. That's really where we get our power. But the fuel it's not an explosion, it's a steady, rapid burn. It's not like as soon as it fires, all the gasoline catches on fire. It doesn't catch on fire all at once. It takes some time to catch on fire, which is why we turn on the spark plug just a little bit before the piston comes up on a compression stroke. As the piston is going down, the fuel is still burning, so the pressure is still pushing on the piston until it gets about all the way down. So the power stroke is where the piston gets pushed down because of the fuel burning and increase in pressure, causing a force to be applied to the piston. During the exhaust stroke, that's where the piston is coming up. The intake valve is still closed. The camshaft or the cam lobe, that bump, is pushing down and on the exhaust valve, and it lets the exhaust gases out. And the piston is coming back up and pushing the exhaust gases out. And so that finishes the 4 strokes and 5 cycles. Here's a nice animated GIF. Let's see if I can catch it here. There's the exhaust, intake, compression, ignition, power, exhaust. Intake, compression, ignition, power, exhaust. Intake, compression, ignition, power, exhaust. So if you need to run that slower, go right ahead. You can see the cams spinning around. You can see the intake valve shortly here. You can see the intake valve opening up and then closing for compression. You can see the connecting rod right here in green. It's going around and around. You can see the crankshaft is spinning. Excuse me. Here's a cutaway of an engine. They cut away a Lycoming. You can see the piston over here. They cut 1/4 of it out. You can see the connecting rod right here. Here's the crankshaft. And let's see if we can get it to go here. Well, doesn't look like it wants to go. Let's try again. Let's go back one more. Well, I guess I'm not going to get it to work. Darn. Worked before. Not today. Okay, let's talk about the horsepower coming out of the engine. Horsepower is the amount of energy that's available. An O360 can put out 180 horsepower. You notice that there's a ratio, 360, 180. Generally speaking, it's a 2-to-1 ratio on the volume of the engine, the cubic displacement versus the horsepower. And it's determined by manifold pressure. By manifold pressure, the higher the manifold pressure, the more horsepower you're developing. Now, there are limits on that manifold pressure, and it's been derated. That is, it's less than what it could actually do. So derated means that you're deliberately putting a limit on how much horsepower it can put out that is less than what it can actually do. Lycoming said, if you want it to make the 2200 hours, which is what a whole bunch of other parts on the helicopter need to be overhauled at, if you want it to go to 2200 hours, then instead of putting out 180 horsepower, where maybe it would only go 1600 hours, or maybe 2000 hours before you had to overhaul it, if you want it to go to 2200, then don't get more than 145 horses out of it. So that means that we're not going to be allowed to go to as high a manifold pressure as you would otherwise. So that's what Lycoming said you had to do to get to 2200 hours. Then Robinson says, okay, we want to design, I'll get back to this here in a second. We want to design, want to have an engine that'll fit our design. And the airframe, the drivetrain, the rotor system, the clutch, all of that can only take a certain amount of stress because we don't want it to weigh too much. If we make it weigh more, it could handle more stress, but if we make it weigh too much, then the helicopter will weigh, the empty weight will be too much, we won't be able to haul anything around. So Robinson decided that if we want to have the lowest amount of weight that can handle a certain amount of stress and still fly well, then Robinson's gonna say you can use 131 horses for 5 minutes, and then you can use 124 horsepower maximum continuous. One of the advantages of having it capable of 180 horsepower and then derating it for 131 to 124 is that the higher you go, you can still maintain 131 or 124 horsepower. So it's not perfect. At a certain altitude, you're still not going to be able to get 131 or 124 horsepower, but the engine is not as susceptible to high density altitudes as it would otherwise. Now, that doesn't mean the rotor system isn't sensitive or affected by density altitude. It starts getting affected as soon as you start leaving sea level, which is why if you look in the performance charts, you'll notice the aircraft does not work as well as you go away from sea level, even if the engine can produce the 131 or the 124 horsepower. So here's what's interesting. Let's look at sea level. On a standard day at the sea level, it's 15 degrees Celsius, so it'd be about halfway between here, 22.3, 22.6. Halfway there, it'd be 1.5, 22.45, and we'd add 0.9 to get max to get takeoff power, 23.3 at sea level. Interestingly enough, I'll go back here. If you look at a manifold pressure gauge at sea level, if you looked at a manifold pressure gauge at sea level, it would sit right here at 29.92 inches of mercury if the engine wasn't running. If we start the engine and we let it warm up, and we run the engine up to 100% power, then what's going to happen is we have to pull that air in. Instead of it being at 29.92, it's going to be about an inch less than that. It's going to be at about 28.92. But that would be in violation of this 23.35, 2892 minus 23.35. Let's see how well my math is. 5. There's a whole 5.57 inches of mercury difference. And that's the difference between 180 horsepower and the 131 that Robinson says, well, you don't need to see those numbers anymore. You don't ever have to calculate that stuff. But the engine could, if you rolled the throttle on, certainly at sea level, you could get this 180 horsepower, but you'd be sending so much energy, so much power to the helicopter that the drivetrain and the rotor system couldn't handle it, which is why Robinson has the engine derated. Of course, power output, we've already looked at that. Use the manifold pressure chart. We've already used the chart, and that'll tell you what you can see set on the manifold pressure gauge. Of course, this here says 26. If a standard day at sea level is 29.92, and we were at 5,000 feet, we could subtract 5 and get 24.92, and that's about 25. So it looks to me like this is a high pressure day at 5,000 feet, because I know this picture was taken at Guidance Helicopters at 5,000 feet, and it's reading not about 25, it's reading about 26. So it must be a higher than standard pressure day. The ignition system. You got to catch that fuel on fire. It's not an explosion, it's a steady but rapid burn, and we need to be able to do that under all kinds of conditions. Like old Harley-Davidson's airplane engines have magnetos, or correction, helicopter engines have magnetos, and they have to get that spark to the spark plug, so the use of ignition cables, and you got to be able to control it with the ignition switch, and I'll tell you what the Shower Sparks ignition system is here, shortly. The magnetos, here's a big fat picture of them. They're generally painted black. They're usually made out of aluminum. The housing, that is, the case, if it's not painted, then it looks aluminum colored, kind of silver. And it's driven off of the engine, and it takes that power off of the engine and converts it into electrical energy to run the spark plugs. They're independent. There's 2 of them on each engine. They're bolted into the engine. As long as the engine is spinning, then the magneto will provide electrical power. They have permanent magnets in them, unlike an alternator. We'll get to it when we get to the electrical system, but alternators, you have to give them a little bit of electricity at first to get them to work. Magnetos or generators, you don't have to do that. So you don't have to provide them with a little bit of power because they already have permanent magnets to start making electricity. Like I said, they're geared into the engine, so if the engine is spinning, then the magneto spins and it'll generate electrical system. 99.9999% of the time, it's independent of the electrical system. That is, if you're flying along and the engine's working, both magnetos are running, if the battery quits and if the alternator both fail, then the engine will still work just fine. You could actually, I'm not recommending this, I'm not saying do it, don't do it, but if you turned off the master switch and turned off the alternator, the engine wouldn't know the difference because the magnetos are not rigged into, they're not connected to the electrical system of the aircraft. Here's a picture, close-up. Here's the firewall going above the engine compartment. That's made out of stainless steel. Here's the firewall in front of the engine compartment. So this is forward and this is up. Here's the oil filter. You can see one of the engine mounts. Here's the back of the engine. You can see some ignition cables going to the spark plug. Here's the oil filler neck and the yellow lid and oil dipstick. It seems to be missing. And here is the magneto. This one has a data plate on it that's made out of blue, but the magneto is right here and it's bolted into the engine. A little more on magnetos. Of course, each cylinder has 2 spark plugs. I've already shown you that. Each magneto operates one, so let's just say here's our engine, and we'll look at it from the side. And here's our cylinder with the cooling fins on it. I know, my lovely pictures. There's a spark plug coming in here and a spark plug coming in here. And let's say we're looking at the back of the engine, and here's a magneto and here's a magneto. So this magneto is going to be powering this spark plug, and this magneto is going to be powering this one. So if this magneto completely quits, we'll still have this spark plug firing into this cylinder. It won't work quite as well because it's designed to run off of 2 of them. But that's the FAA requirement, is you have 2 independent ignition systems. That's why there's 2 magnetos and 2 spark plugs. Well, 2 magnetos per engine, 2 spark plugs per cylinder. And of course, when the engine's rotating, the magneto generates the spark. 2 magnetos, each magneto fires all 4 cylinders, so therefore there's got to be 8 spark plugs. The ignition cables. Here's a picture of some ignition cables. Here's some magnetos. Here's some ignition cables. and the connectors that go into the spark plugs. Ignition cables take that high voltage. It's about 20,000 volts, just for fun. It's enough to give you a zap, but the amperage is really low, so it's not going to hurt you. Well, it won't damage you, but it will make you jump. You can see that there's a spark plug right here going into the top of the cylinder. There's a spark plug going here, and this cable right here would go to one magneto, and this cable would go around back to the other magneto. Of course, here's a big picture of a spark plug. Electricity is going to come in. There's insulation inside. It's going to go from the electrode over to the other one. And right at that spot right there, there's going to be effectively a little lightning bolt, a bolt of lightning. And if there's fuel and air mixture right there, it's going to catch them on fire, and the flame's going to spread out to the rest of the inside of the cylinder. And again, you already know where the spark plugs are. And here's a picture of the cowling taken off of an R22. You can see one of the ignition cables coming in here to the top spark plug, and the ignition cable coming here to the bottom spark plug. This is a good view. You can see the cylinder fins, the cooling fins, and the air. Like I said before, the air is going to come in and blow across it. And it makes that noise. Okay, let's talk about that ignition switch. The ignition switch is on the instrument panel just below the engine gauges. We'll do a close-up right here. Here is the ignition switch. You notice it's off. That's where we leave it most of the time. Right, left, both, and start. If you rotate it to both, that means both magnetos are turned on. If you have it in left, that means only the left one is working. If you go to right, only the right one's working. And just you put a key in there, and if you rotate it all the way over to start, then you'll also engage the starter, and you'll engage the shower sparks ignition system, or the vibrator, the starter vibrator, and we'll get to those details here shortly. Here's a picture of the engine RPM gauge. Whoops. There we go. You're going to do a run-up check. After you start the engine, you're going to check. You're going to do a magneto check. You're going to do a magneto check. You're going to run the engine up to 75% of its RPM, and then you're going to turn one of the magnetos off, and you should have no more than a 7% RPM drop in 2 seconds. So you're going to hold it there for 2 seconds and see, make sure it doesn't drop too far, and then you're going to try the other one. So now we'll take a peek here. So there's the ignition switch. Here's the RPM gauge, and here's the ignition switch. So what's going to happen is after you get the engine running, it's going to be in both, and you're going to let it warm up. Then you're going to rev the engine up to 75%. Of course, the rotor RPM is going to come up with it. And then what you're going to do is you're going to rotate the ignition switch over to the right magneto. Turning it to the right turns off the left magneto. So you're going to see the RPMs come down. You can only let it come down 7% in 2 seconds. So you're actually going to turn it to right, count 1 Mississippi, 2 Mississippi, and you're going to keep track of how far it goes down. As soon as you get to 2 Mississippi, you're going to rotate it back to both, and you'll be watching the RPM gauge. You're not going to be watching this. You're just going to go click over to right, and you're going to see how far, and you're going to go 1 Mississippi, 2 Mississippi. If it doesn't go down below 68, then you're good. You've turned it back to both. The RPMs are going to come back to 75. Then you're going to rotate it over to the left magneto and count for 2 seconds. It'll start dropping when your 2 seconds is up. You rotate it back to both, and then the RPMs will come back up, and that drop, when it was on the left magneto, can't be more than 7%. So if you get less than 7% drop on the right magneto and less than a 7% drop on the left magneto, then that means that it's working well. Each magneto is working well. And of course you're going to leave it in both for the rest of the time. So that's finding out, confirming that both of the magnetos and the spark plugs and the ignition cables are working correctly. Now, the starting vibrator is also called the shower sparks ignition system. The shower sparks ignition system means that when during start, inside of the cylinder, you're getting a shower of sparks, a whole bunch of them, and not just one. That makes it easier for the engine to start. Here is a box. This is on the right-hand side of the helicopter. This is looking forward. This right here is the stainless steel firewall. And this is the shower. This is the starter vibrator, one of the components of the shower of sparks ignition system. And you're kind of wondering, well, I've never heard of the shower of sparks ignition system. What's up with that? Here, I'm going to go to red. Why is it needed? Well, when the engine is spinning slowly, the magnetos don't work very well. You got to spin around a generator pretty fast to get enough electrical power out of it to do any good. So when the engine is being cranked over by the starter motor, the engine doesn't spin around very fast, so the magnetos don't spin around very fast. So it's needed because the magnetos don't spin around very fast while the engine is getting started. We need a different method of generating electricity while the magnetos are spinning slowly. So this starting vibrator is going to help do that. It's going to take electrical power from the battery system. It's going to take electrical power from the battery system and run that battery power into the magneto. So instead of the magneto spinning fast enough to generate its own electricity, it's going to use electricity from the battery, but only during start. Let's see. Let's take a peek here. Let's look at inside of a cylinder. And we'll say we're on the compression stroke, and the piston is almost all the way up. And it works off of the left magneto. The shower of sparks only is working with the left magneto. And what happens is this magneto here, and we've got our vibrator and retarded points, it sends electricity to the magneto. And the magneto increases the voltage from that 12 volts up to 20,000 volts. Woohoo! And runs it into the spark plug. Now normally when the engine is running, this system doesn't work. This only works when the ignition switch is in start. The magneto is spinning around and around, and it generates its own 20,000 volts. And it only runs it to that spark plug once. Just before the piston is almost all the way up, it'll fire that spark plug, and it'll only fire it once. During start, when we're using the shower sparks ignition system, this vibrator, the reason it's called a vibrator is because there's a relay in there that goes back and forth. If you're actually touching this, you'd feel it vibrate. It sends a bunch of pulses of 12 volts to the magneto, so the magneto converts each one of those 12 volt pulses into 20,000 volts. So while the engine is spinning slowly, instead of just sending one spark to it, it sends a bunch of sparks. If you were watching that spark, instead of just having one, have it fire just once, you'd see 3, 4, 5, 6, 7, 10 or 20 times. You'd see a bunch of them. That's where they get the shower part, is because there's a whole bunch of sparks occurring, and this makes the engine much, much easier to start by getting a bunch of sparks during the starting sequence instead of just one. So that's a big advantage to having a shower sparks ignition system, is you get a whole bunch of sparks during the starting sequence. Now remember, the only time that we're using battery power in the ignition system is when you're holding the start switch in the start position. As soon as you let go of that, it's because the engine is spinning and the magneto works by itself, and we're not using the vibrator. The vibrator's not sending 12 volts to the magneto anymore. First, the carburetor and induction system. The main components of the carburetor and induction system are the carburetor. Here's a picture of a Marvel Schebler carburetor on a Robinson R22. The carburetor, this would be the front of towards the front of the aircraft. This right here, where this arm sticking up, is the mixture control, and that controls or changes the ratio of fuel to air. And this is the throttle right here. You can see the throttle butterfly, or the throttle valve sticking up. So as you push forward or pull back, this opens or closes and lets more or less air in. Here's a picture of a throttle installed on a Robinson R22 helicopter. Here's actually the throttle push-pull tube coming in to move the throttle back and forth. And it's hard to see, but there's actually the mixture control right here. There's a shaft goes down right in there. There are induction tubes, and that gets the air from the carburetor up to the cylinders. It's hard to see in this picture, but here's the ends of the cylinders, and here are the induction tubes, and the carburetor air box is down here. There's the carburetor, and then there are tubes that go through the middle of the engine oil sump to let the air go into the cylinders. And here's another picture. Here's a picture of an engine on its side. You can see, or looking at it from the bottom up, here's the carburetor, here's the air, and this kind of a carburetor is called an updraft carburetor. It actually goes through it, and inside, this is actually the bottom of the engine. On a car, you would have called this the oil pan. This is the oil sump at the bottom of the engine where the oil drains down into, and there actually is ducting. There's a tube there, and then there's a tube over here. So the cylinders on this side of the engine, one over here, whoops, one over here, and one over here. So that picture didn't work out too well. In any case, there are 4 ducts inside the engine sump, one for each cylinder. You can't see the ones going through the engine on the other side. Of course, you need an air filter. Keeps out dirt, dust, grime that would go into the engine to make it wear out sooner. The carburetor air box, or carb air box, it's mounted on the bottom of the carburetor. This is a picture of an R22 looking forward. This picture is taken from about a foot and a half off of the ground. You can see the oil sump of the engine. You can see an induction tube going up. You can see an exhaust tube going out, and here's the carburetor air box right here, and air goes into it, and then it goes up into the carburetor, and just before the carburetor is an air filter, and then of course the carburetor would sit right here. And here's another picture of the carburetor air box. You can see that under normal circumstances there's a grill right here, so big things get weeded out. It won't pull up weeds. That's corny. Air comes down into the carb air box and then goes up through the filter, through the carburetor, through the engine oil sump tubing, and then into the induction tubes into each of the cylinders. Here's another picture of the carburetor. You can see here again is the push-pull tube going for the throttle. That's connected directly to the twist grip throttle and the correlator, and of course the governor also move it. Here's the carb air box. You can't see it, but there's actually an air filter in here, so the air has to go through the filter before it can get into the carburetor. This is actually the bottom of the engine, the oil sump, and you can barely see it, but there's a lever right here, and this is the mixture. So when you move the lever in the cockpit, it'll move that. Basic operation of a carburetor. This is a very simplified version of a carburetor. This is an updraft carburetor, like I said, in this airplane, and in this aircraft, in this helicopter, and in many other aircraft. They are updraft carburetors. The carburetor is mounted on the bottom of the engine. The air goes up through the carburetor. I guess that didn't work out. It wasn't really a good one. Oops, that's the one I wanted to get rid of. In here you can see the fuel. These dots in here is the fuel. This part right here, float chamber or the carburetor bowl. And fuel comes in from the fuel tank. Goes through here. This float right here has air inside of it, and it's sealed. And so if the fuel level goes too low, it goes down. This little needle lifts up, and more fuel can come in to keep the fuel level at about the same place all the time. The basic operation of a carburetor is that there is a venturi. You'll notice that there's a curved part right here and a curved part right here. As air goes through this venturi, it speeds up and the pressure goes down. You're going, what? Here, let me give you an example. Let's say you have a garden hose and you stuck your thumb across it. So you have some blue fingernail polish. You would be reducing the area of the available nozzle, and the water would squirt out faster. So effectively, you've taken this water duct and you've stuck your thumb across it, and so this area right here is smaller than it used to be. So you've actually created a venturi. So the velocity of the water, the velocity goes up. But according to a guy named Bernoulli, we'll get to that later when we get to aerodynamics, the energy in each molecule stays the same. So if we increase its velocity, energy due to velocity, then we have to get this from somewhere else. And what happens is the static pressure goes down. So in a venturi right here, the velocity goes up, the static pressure goes down, and the fuel in here, see the fuel in here, the fuel in here gets sucked out because the pressure in here may be 29.92 inches of mercury on a standard day at sea level, but if in here it's at 27.92 inches of mercury, it's at a lower pressure, so it's going to suck the fuel out. So it's going to suck the fuel out of this nozzle, and the fuel is going to immediately start evaporating on its way to the engine. When you move the throttle, you're moving this throttle valve or butterfly valve back and forth. Right now it's mostly closed. If you had the throttle full open, it would be in this direction right here, and air could get past it really, really easy. The airflow would be fast, or you would have a large volume of airflow, and of course with more air going past the nozzle, it would suck in more fuel. So the carburetor is set up so that the more air goes past the venturi, the more air goes past this nozzle, the more fuel comes out. The more fuel it comes out, the more horsepower you're going to have. Of course, you also need the air. When you get into the engine, you need air and fuel. So as you change the position of the throttle, if you change the position of the throttle to where it is right now, then only some air can get past it. Only some air can get past it. And this would be at a low power setting, so only a small amount of fuel would leave the nozzle. So small amount of air, small amount of fuel. Large amount of air, large amount of fuel. So it maintains this ratio of fuel to air, and you have complete control over the volume of air, and the carburetor is deciding how much fuel to squirt in. Also, you notice this gizmo over here, this is also hooked up to the throttle, although the linkage doesn't show it, but it's an accelerator pump. I'll abbreviate accelerator pump. And if you drive an old school car or truck, they're on the pump. You push down on the throttle with your foot, and it squirts fuel in. What ends up happening is that when you push the throttle forward, a little bit of extra fuel gets squirted in. And so it makes the engine accelerate a little faster, it keeps it a little cooler, and the engine doesn't run lean. Lean means there's too much air for the amount of fuel. Rich means that there's a little bit too much fuel for the amount of air. So on the carburetor that's in an R22, we do have an accelerator pump, so you can actually rotate the throttle and squirt some extra fuel into the carburetor for engine starting. Okay, we'll just keep this carburetor in the corner. So, what is the point of having a carburetor? It's there to change how much air and fuel go into the engine. And that's when you do the twist grip, that'll change the setting on the throttle valve, or sometimes called the butterfly valve. It also controls this ratio. The fuel-air ratio is also called the mixture. And that's the ratio of fuel to air. I think it's on the very next one. Yep. Oh, I'll get to it. The problem with carburetors is that they measure volume of air. It's only basing how much fuel comes out based on how much volume of air goes through it. The problem is, as we go to high density altitudes, the air is less dense. We may pull a cubic foot of air through the carburetor and go to the engine, but there's not as much air and as many air molecules, so we're actually going to be pulling in a little bit too much fuel. That would be a little bit rich. So the higher we go in density altitude, the higher the altitude, or the hotter the day, then the engine's going to run a little bit on the rich side. Same amount of volume of air, but not as many molecules in a cubic foot. So we're going to have to take that into account, the fact that this carburetor, with this venturi, is only using the volume of air. So we have to, cover that. We're going to have to take care of that mixture, and we'll get to that on another slide. Idle cutoff. Another part of the carburetor, and it's drawn in another picture here, is this fuel going in. There's effectively a shaft with a pointy part on the end. And when you you lift this up, then fuel can go in. When you shut the engine down, you're going to pull the carburetor heat off, the mixture rather. You're going to pull the mixture, and you're going to push this all the way, end up pushing this down, and it's going to cut off all the fuel to the carburetor, and so the engine's going to starve of fuel, and that's actually how you shut the engine down.
R44 transition training.
Engine specifications. It's still made by Lycoming. It's just got 2 extra cylinders on it. And the engine in an R44 is an IO540-AE1A5. Excuse me. It's got 6 cylinders. Like I said, it's horizontally opposed. That's what this O is for horizontally opposed. So if we look at the engine from one side, there's a piston on one side, a piston on the other. And you could say that these pistons oppose each other, hence the O. Yeah, I got any hints. Direct drive means there's no gearbox. The inside of the engine, the crankshaft comes straight out of the engine without a reduction. It's air-cooled, just like an O360. It's fuel-injected, so here's the big difference. Instead of a carburetor, it's fuel-injected. We're going to talk about that before this video is over. And normally aspirated means it's not turbocharged and it's not supercharged. Oh, by the way, fuel-injected, the I right here stands for injected. And of course 540 stands for how many cubic inches of an engine that is. So that's a lot bigger than a small block Chevy with 350 cubic inches. At sea level, if the engine wasn't derated and you ran it at red line RPM, that's the red line of the manufacturer of the engine, not the red line on the RPM gauge. In the helicopter, the actual red line is higher. Out of Lycoming, you could get 260 horsepower out of it. Just like the R22, there's a 5-minute takeoff rating. In this case, it's 245 horsepower, and for the rest of the time, your maximum continuous power is 205 horsepower. Instead of a smaller amount, this engine's bigger, so it takes 7 to 9 quarts of oil. That is, you're going to add oil when it goes below 7 quarts. Here's a picture of a Lycoming IO540. This engine is very similar in that the airflow to the engine comes up through the oil sump and then goes through the intake ducts to each cylinder. The big difference is instead of a carburetor down here, there's a fuel injection control unit, and it sends fuel. Well, I'll talk about that a little bit later. But look, 1, 2, 3 cylinders on this side, 1, 2, 3 on the other, starter ring, place to bolt stuff on. It's just a big O360. Effectively, it's just an O360 with a couple of extra cylinders bolted on. Actually, the biggest difference between the engines, other than having a couple of extra cylinders, is that it's fuel injected instead of a carburetor. And you got to understand that the fuel injection system on a lot of cars and diesel vehicles are set up. Let's say here's our piston inside of a cylinder. See how well I can draw today? Pretty poorly. In most fuel injection automobiles and cars, there's a fuel injector that squirts the fuel directly into the cylinder. That is not the case in aircraft engines. Aircraft fuel injection engines, fuel-injected engines, have an intake valve, and they've got the induction system, and it actually squirts the fuel in just before the intake valve. Now, of course, here's the metal of the cylinder. Here's the metal of the cylinder. So it's not drilled into the intake tube. It's this hole where the injector goes in is actually drilled into the metal of the cylinder, and it squirts it in just before the intake valve. So when the intake valve opens, the air and the fuel come in. When the intake valve closes, the fuel injection continues. It's a continuous fuel injection system. In a lot of cars and diesel engines, the fuel injection turns on and off. So during the intake stroke, it squirts fuel in and then it stops. But in aircraft engines, the fuel injection system runs continuously. But by the time this speeds up and the engine is running, you really can't tell the difference. The fuel control unit. If we had the engine, they're sticking out with a crankshaft, and we've got cylinders sticking out, and here's the sump, the fuel injection system is going to be down here, and the air is going to go up to all the cylinders, and there's a butterfly valve in here, but interestingly enough, there's no restriction, there's no venturi. Air goes through here into the engine, And this fuel control unit, fuel comes in and goes around to the flow divider on the top, and then from the flow divider it goes to each of the cylinders. So the air goes in the intake. Obviously, just so you know, there's going to be an air filter. It measures how much air is going in, but it's measuring it by volume. So this airflow in here is measuring volume, just like a carburetor does, which means the mixture is going to be messed up at different altitudes. So we have the same restrictions. You're not going to want to, let's put it this way, at guidance helicopters, no one ever touches the mixture control in flight. And on the ground, the only time anyone may operate the mixture control is if they are an instructor or they are doing it under the supervision of an instructor. So if you ever solo, you're never going to touch the mixture control on the ground, and you're never going to touch it in the air. If you're with your instructor, you're only going to touch the mixture control, or your instructor's only going to touch the mixture control while you're on the ground. So we got injector nozzles, a fuel control unit, and the mixture control. Here's a picture of a cylinder. Here's the oil drain. Here's the oil drain line. So oil at the top of the cylinder come out. And this is the tube where the air would be coming in. This engine doesn't have a fuel injector, but this is the hole where the fuel injector would be squirting fuel in. So as the air comes in and goes into the cylinder, it grabs some air. And here's maybe a better picture. So here's our fuel control unit. And there's a butterfly valve in here. And a fuel line comes in. And there's a mechanism in here. And the fuel actually goes to the flow divider. And then through these little tiny lines. And I can't remember if they go in at the, yeah, they're going to go in here somewhere. They go to the cylinder. So the fuel is actually going to the cylinder separately than the airflow. If you get a chance, when you see the cowling off of an R44, go out and take a look and take a peek at the fuel system. Big difference between the fuel system in a Robinson R22 and an R44 is that there are fuel pumps. In an R22, gravity is the only thing that pushes or pulls fuel into the carburetor, but fuel injection systems need high pressure fuel to work very well. And we wouldn't want, if you only had one pump, for that pump to quit and then the engine not work very well. So that's why there's two pumps. So if one fails, the other one will continue to work. The engine-driven pump is bolted into the engine, and you cannot turn it off. You cannot turn off the engine-driven pump. The electric pump, or auxiliary pump, or aux pump, has an electrical switch, goes through the clutch. If the clutch is on, you can turn on the electric boost pump, the electric auxiliary pump, and it'll work that way. And I think it's on the next line here. Ta-da! If either pump quits, just one pump working after that makes the engine work just fine. You get full engine performance. So that's pretty good news. This diagram is probably too yucky for you to see on the video, but we're going to have a fuel main tank, and we're going to have an aux tank, and fuel's going to come down to, let's see, where's the gasculator? Fuel's going to come down to the gasculator, and there is an engine-driven pump which runs off the engine, and there's an electric boost pump, and fuel goes to both of them. And both of them can provide fuel pressure to the fuel control unit, and then it goes up to, yeah, I think this is pretty pointless for me to be drawing. Never mind. Fuel pump failures. There is not a warning light for the mechanical fuel pump. There is not a warning light for the mechanical fuel pump, but there is a low pressure light that's called the aux pump warning light. That tells you that the aux pump either isn't working at all, or it's too low of a pressure to be doing any good. Like I said before, the aux pump only works if the clutch switch is on. This works out really nice. That way, when you start the engine and the clutch switch is off, the aux pump is not on. So that means the only way fuel can get to the engine is if the mechanical pump is working. That way, when you start the engine and it does start, that tells you, aha, the mechanical fuel pump is working. Then, after you get the clutch switch on, you can turn on the aux pump, and if the aux pump light goes off, that tells you the aux pump is working. Also, when you shut the engine down, when you turn the clutch switch off to disengage, that'll turn off the auxiliary pump. If the engine still runs after you've turned the clutch switch to disengage or turned the clutch switch off, that means the mechanical pump is still working. So you're finding out twice per flight, just after you start the engine and just before you shut the engine down, you'll find out if the mechanical pump is working. Of course, like right here, if the mechanical pump isn't working, the engine won't start. That's how you know if the mechanical pump is working. And if you're shutting the engine down, prior to shutting the engine down and you turn the clutch switch off, if you turn the clutch switch off and the aux pump goes off and then the engine quits immediately, that'll tell you the mechanical pump isn't working. There is a relief valve set up, so because both pumps working simultaneously pump more fuel to the engine than is needed, so that extra fuel actually returns to the auxiliary fuel tank. So the auxiliary tank is where any extra fuel coming off of the pumps ends up. That means there's more fuel lines than there is in an R22. Okay, fine. There is a fuel filter, a separate fuel filter in an R44. In an R22, there's the gasculator, which is a very, very, very fine metal screen, and there's another metal screen going into the carburetor. But carburetors can handle a little bit of sediment, a little bit of crud, and they'll still work okay. Fuel injection systems, it's the nozzles in particular, that they can get clogged up much more easily, and they won't spray the fuel like they're supposed to, and the engine won't run as well. So there is an additional fuel filter in an R44 to filter out all the sediment just in case, so the fuel nozzles don't get clogged up. And if the fuel filter gets clogged up, there's a bypass valve. There is a bypass valve so that fuel will still get to the engine even if the fuel filter is clogged. If the fuel filter is clogged, the fuel filter warning light will come on, but that does not mean that the engine is going to quit right away. It just means that it's not filtering the gasoline anymore, and you need to have maintenance done. The startup procedure is a bit different because fuel-injected engines start differently. Interestingly enough, you're going to prime it, and then you're going to actually pull the mixture all the way out and crank it with one hand, and when the engine starts to start up, you're going to push the mixture in. It's pretty funky. I'm not going to get any details other than James Brown designed the startup procedure, and that's why it's so funky. No carburetor heat. The fuel injection control box, the fuel injection control, doesn't have a venturi in it like a carburetor. Remember that there was two ways why you would have carburetor ice, and one is the venturi, the air goes faster, so if the velocity goes up, the pressure would go down. If the pressure goes down, water can go from vapor to ice much, much easier. Also, in a carburetor, we had the fuel nozzle in here, and it was squirting fuel out, and as the fuel evaporated, it takes energy out of the air and any water vapor in it, and that water vapor might actually go from a water vapor into ice. So that was the two ways how you could get icing in a carburetor. But in a fuel injection system, we don't have any of this. There is a butterfly valve in here, but there's no venturi, so that one of these ways to get carburetor heat isn't there. And since there's no fuel getting squirted in here, remember the fuel's getting squirted right into the cylinder just before the intake valve. There's no fuel getting squirted in here to evaporate, so that gets rid of the second way you can have carburetor ice. So fuel injection systems are not prone to carburetor ice, so there's no carburetor heat. However, your instructor is probably going to recommend, since you're going to be flying R22s after you're done flying R44s probably, they're going to suggest that when you're doing checklists, and in an R22 where you would normally consider pulling out the carburetor heat, you're going to say no carburetor heat is necessary, or some other phrase to keep you into the habit pattern of thinking about carburetor ice and using carburetor heat.